Hi everyone, so today we are going to be talking about solution chemistry. So first let's start off with some basics about some properties of solvents. So water has these properties, especially surface tension and capillary action. And these are unique properties of water and they are effects of its polarity because water is polar and its polarity gives it many unique capabilities such as cohesion, adhesion, surface tension, capillary action, and also its very high specific heat. Its specific heat is 4.184, which is extremely high compared to that of some other metals. So what is capillary action? So basically capillary action occurs when adhesion is stronger than the cohesive forces. So for example, if you have a tube, like a glass tube, water will come inside the tube and it will stick to the sides of the tube, causing it to move up. And you've probably seen capillary action before if you've ever done one of those plant experiments where you put a plant in colored water and you observe how the colors move up to the colors of the petals and how you can observe that color. That's capillary action. So that's a property of water. Another thing is surface tension. And surface tension is tension in the particles or tension in the surface particles that are caused by cohesive and adhesive forces. So cohesive forces are what makes water stick together. So cohesive forces are between one water molecule and another water molecule. And then adhesive forces are when water sticks to other things. So the combination of them creates surface tension. And as you can see, this bug on the pond, water is has very high surface tension, so you can kind of sit on it without it breaking. Similar if you've ever done a penny experiment where you put drops in a penny and you see the little bubble on top, usually can fit about 30 drops in a penny. That's all because of water's surface tension. Okay, so let's talk about these phase diagrams. So phase diagrams observe changes in states and things like that through the different phases of matter. So over here, so this is our solid phase. So this is when your substance is going to be a solid. So as you can see, it kind of looks like, this looks like a triangle here. It's like almost like a Y. So over here we have our solids, in the middle we have our liquids, and then anything here is a gas. So we have some important points here. We have our triple point. So the triple point is when a substance is everything at one time. So at this point here, whatever this is, I'm assuming it's water, it's going to be a solid, liquid, and a gas all at once. So you will observe it freezing and you'll observe it boiling, creating gas particles. If you look it up on YouTube, you can see all these cool videos about water at its triple point. But basically, it's going to be melting, it's going to be boiling, it's going to be creating gas all at the same time. And then we have our critical point over here. And so the critical point basically means that anything after this point is going to be a gas. So that's the extent of which you're going to have a liquid here, and then anything after here is going to be a gas. And then here you can kind of tell your phase changes. So a solid will turn into liquid at this point. And then, so that would be vaporization. And then boiling would be here, your boiling points, when it turns from a liquid to a gas, and then you can measure it at different pressures. So at 1 atm is the common way you measure your boiling and melting point. And then here, so if you're going from a solid directly to a gas, that would be sublimation. So this is where you're subliming, and then this is where you're creating deposition, or you're creating that solid there. Okay, so now let's talk about these things called solubility diagrams. So these are very important. So here we have all these different compounds. We have sodium nitrate, we have calcium chloride, lead nitrate, and these are all telling us the solubility of these different compounds at different temperatures. So for the most part, solubility tends to increase as temperature increases, but that's not always necessarily true. So when we're looking at this diagram, we can see, pay attention to the axes. So this is solubility, grams in salt of 100 grams of water, and then our temperature. So if we were to say how much grams of a salt of, let's say, sodium chloride dissolves at 20 degrees Celsius. So we would go over here to 20 degrees Celsius and we would go up and we would see that it's about 35 grams. But if I asked you, say, this is why you really need to pay attention to your axes. Because if this is 100 and I asked you for 200 or 300 grams of water, you would need to double or triple that mass of the sodium chloride. Something else that these diagrams can tell us is the line represents when the solution is saturated. So when the solution is saturated, it means it has as much solvent as it can hold without it being supersaturated. And supersaturated means it has more solvent dissolved than it can possibly hold. And you're probably wondering, how can something be supersaturated? Well, as you know, when we increase the temperature, we can increase solubility. So we can keep increasing the temperature to try to dissolve more things than we actually can. So let's see, for instance, NaCl. So at 20 degrees Celsius, it's saturated with 35 grams. But if we go up here, anything above it would be supersaturated, and anything below the line would be saturated. Same thing for anything else. Sodium chloride, anything above is supersaturated, below is unsaturated, and just on the line would be saturated. Okay, so now let's do some math with these calculations, or this information that we know about solutions. So you should remember the molarity formula, and remember that molarity is equal to moles divided by liters. And so we can use that to solve dilutions. And what dilutions are is you have initial molarity, molarity 1, and then you have an initial volume, volume 1, and you're setting up basically an inverse proportion. So molarity 1 times volume 1 equals molarity 2 times volume 2. So basically what you're doing is if you have a certain volume with a certain concentration, you're trying to see what would happen if you added more water or if you added a higher concentration, and see how that would affect the molarity or the volume. So let's see what this says. So it says we have 100 milliliters of a 2.5 m molarity sodium bromide solution on hand. So now we need a 0.5500 molarity. So what is the final volume of the solution? So now we know that we're looking for V2. We're looking for the final volume. So let's start with our calculation. So we have 100 milliliters. And then we know that it's a 2.5 molar solution. Now, we know that we need it to be a 0.55 m solution. But we don't know the volume. So it's going to be a basic algebra problem. So now we multiply, when we multiply 100 by 2.5, we are going to get 250. And then that's going to be equal to 0.55x. And then we can simply divide, and we can get that x is going to be approximately 454. Now let's be careful of sig figs here. So do you remember sig figs? Let's see. So we have 1, 2, 3, 4 sig figs here, 1, 2, 3, 4 sig figs here, and 4 there. So we're going to use 4 sig figs in our final answer. So 454.5 milliliters of solution. So that's going to be our final answer there. Okay, now here's a dilution problem. I'd like you to try it on your own. If you could just pause the video, see if you can do this, and then I will explain it real fast. All right, let's see how you did. So we have 2 liters of a 0.8 molar solution of NaNO3, and it must be prepared from a solution known to be have a 1.5 molar in concentration. So how many milliliters are required? Okay, so we know that we have 2 liters. And we know that we have 0.8 m. And now we know that we want 1.5, and we want to know the milliliters. So one more thing. We got to be careful of our units here, because this is in liters, not milliliters. The good thing about the dilution formula is it's not like the molarity formula where it must be in liters, but you do have to be aware of your units if you use 2 different units. So let's go ahead and convert this to milliliters. So this would be 200 milliliters, because we want our final answer to be in milliliters. So 200 times 0.8, that's going to be 160 milliliters. Or not milliliters, just 160, because it's m times liters. And then we have 1.5x. And then we're going to do 160 divided by 1.5. And then our x, which is the milliliters, is equal to, remember sig figs again, 3 sig figs in each problem. So we're going to have about 107 milliliters. And that's going to be our final answer there. All right. So now let's talk about some acid-base stoichiometry or solution stoichiometry. So what's different about solution stoichiometry is we are going to be incorporating not only moles in our moles to grams to atoms to conversions, but we are also going to be using molarity and milliliters in those formulas and how we can incorporate those mole ratios. So this problem says how many milliliters of a 0.2 m hydrogen phosphate or phosphoric acid solution is needed to react with 100 milliliters of 0.1 NaOH. Okay, so let's start with our known. So we know that we have 100 milliliters here, and we know that we have 0.1 M. And then we also know that we have 0.2, but we don't know how many milliliters. So we are always going to start with our known, which we know both things. So that's going to be the sodium hydroxide. So let's go back to our molarity formula. Everything goes back to the molarity formula. Molarity equals moles over liters. So we have 100 milliliters. So how many liters are in 100 milliliters? 0.1 liters. Perfect. So we are going to have 0.1 M is equal to X moles over 0.1 liters, which is just going to be 0.01 moles. So now that we have moles, it's going to be really easy to compare our ratios stoichiometrically. So we have 0.01 moles of NaOH. Excuse my messy handwriting. And so let's look at our balanced equation. So usually they wouldn't give you the balanced equation. You would need to find it yourself. But we have a 3 here. So that's going to be 3 moles of NaOH for every 1 mole of phosphoric acid. All right. So 0.01 divided by 3, we're going to get about 0.0033 moles of H3PO4. Okay, so now it says how many milliliters. So now that we know the moles, we can go back to our molarity formula. So it says here that we have a 0.2 M solution. So that's going to be 0.2, oops, did I zoom in? Let's see, hold on. All right, there we go. Okay, sorry about that. So we have a 0.20 M solution, and then that's going to be equal to moles over liters. So we have our 0.0033 approximately. If it's in your calculator, make sure to use the actual decimal. You will get a more accurate answer, especially with sig figs. And then moles over liters, which is what we don't know. So we're going to have 0.20x is equal to 0.003 moles, 33 moles. So we're going to put that answer in our calculator. We're going to divide by 0.2. So we're going to get approximately 0.0166 liters. But the problem, as for milliliters, we always need to be careful of our units. So we're going to multiply through by 1,000, and we are going to get about 16.67 milliliters. Now let's look at our sig figs. 100, 0.1, and 0.2. Well, does this 100 have a decimal? No, that's just one sig fig. But we can go ahead and be a little more accurate and say that there's about 17 milliliters. Okay, well, thank you so much for watching, and I hope you learned a little bit about solution chemistry today.